In this video, we're going to take a closer look at lenses. In our closer look on mirrors, we learn strategies to help answer questions about mirrors. Much of that content applies to lenses too. In this segment, we'll highlight those areas and get practice using those approaches with lenses. As you answer questions about lenses and mirrors, be careful to keep in mind which kind you are working with. Though they may look similar in a picture, mirrors reflect light, while lenses refract light. That means the ray diagram for a mirror will look really different from the ray diagram of a lens. Speaking of ray diagrams, they are always part of our approach to answering lens questions. Keep the good habit you begin with mirrors by drawing ray diagrams as you begin a lens question. Before we try a few examples, I will show you a way of drawing lens diagrams that clarify the situation and give you confidence in your answer. In a lens diagram, there are 3 rays we can draw that are called principal rays. These are lines that connect the object, image, and focal points in this scenario. Here's a picture of an object in front of a converging lens. Since the lens bends light coming from either side equally, there are 2 focus points. We can call them F1 and F2. The first principal ray begins at the object and runs parallel to the optical axis until it reaches the lens. The lens then bends the ray so it passes through F2, the focal point on the opposite side. Notice that just by drawing one principal ray, we can't tell where the image forms. It could be anywhere along the ray. The second principal ray runs from the object straight through the center of the lens to the other side. That way it doesn't bend at all, but keeps on going straight through. The third principal ray begins at the object and passes through the first focal point, F1, then onto the lens. The lens refracts the ray so it moves parallel to the optical axis on the other side. These are the rays to include whenever we draw a ray diagram. With diverging lenses, you will use the same principal rays as you can see here. These lenses make an image that is virtual. It can't be projected on a surface. Wherever all 3 meet, that's where the image forms. When the lines diverge from one another, we trace dotted lines from the lens to where they converge on the same of the lens as the object. If 2 of the lines meet up, but the third doesn't cross at that same point, that tells us we need to go back and double-check our work. In general, if our lens diagram is correct, our answer to the question is going to be on target too. Just like with mirrors, the focal length, object distance, and image distance of lenses are related by this equation. 1 over the lens focal length equals 1 over the object distance plus 1 over the image distance. Along with where the image is located is the question of how big it is. This is called the image magnification, capital M. Image magnification equals the image height divided by the object height, or negative the image distance divided by the object distance. When magnification is less than 1, the image is smaller than the object. And when it's greater than 1, the image is larger than the object. If the answer is negative, we know it is inverted. Solving lens exercises requires carefully keeping track of positive and negative signs. This table shows that when the lens focal length is positive, the lens is converging. When the focal length is negative, that means the lens is diverging. If the image distance is positive, the image is real. And on the far side of the lens, as the object, while a negative image distance means the image is virtual, it exists on the same side of the lens as the object. Positive object distance indicates the object is real, and negative object distance tells us the object is virtual. When image magnification is positive, the image is upright, and when it's negative, the image is upside down, inverted. Remember these conventions when you're solving lens exercises. They will help you find the correct result. All right, let's try out some lens exercises. Using a converging lens with a focal length of 22 centimeters, an object is placed 45 centimeters from the lens. Where does the image form? And is it real or virtual? And what is the image magnification? Our sketch of the information given shows the object further from the lens than the focal point F1. Let's trace in the principal rays passing through this converging lens. Remember, the principal rays begin at the tip of the object. One passes through the distant focal point f2, one goes through the center of the lens, and one through the nearby focal point f1. Now you give it a try. Pause the video and take a minute with a ruler and pencil to draw in the 3 principal rays. Then come back and check your work. Okay, we're back, and here's a diagram showing the principal rays involved. In this case, the image is real. It appears on the opposite side of the lens as the image, and it's inverted. Now let's find out its position. We'll rely on an equation we use in the mirror segment. 1 over the focal length equals 1 over the object distance plus 1 over the image distance. To rearrange to solve for d sub I, we'll multiply both sides by the focal length, image distance, and object distance. Then isolate the terms with d sub I, factor that term out, and finally divide both sides of the equation by d sub O minus f. That distance equals the focal length of 22 centimeters times the object distance of 45 centimeters divided by 45 centimeters minus 22 centimeters, which altogether is 43 centimeters. In a minute, we're going to check this answer to see if it makes sense with our ray diagram. Before we do that, let's figure out what the image magnification is. Since we don't know the object or image height, we're going to need to rely on object and image distance. Our magnification equation is a ratio of the negative of image distance to the object distance. That means the image magnification in our case is negative 43 centimeters divided by 45 centimeters, which is negative 0.96. Now we've figured out what the question asked about, but do our answers make sense together? Are they consistent? Let's bring together our ray diagram, the image distance, and the object distance. The ray diagram indicated our image distance will be positive, since it's the opposite side of the lens as the object. It also looks like the image distance and object distance are about the same, and that the image is inverted. The results we find for image distance and magnification confirms this. The object and image distances are about the same, and the image magnification is nearly -1, meaning the image and object are nearly the same size, but that one is inverted compared to the other. This is what we expected, so we can be confident in our solutions. There's more than one sign, they're correct. Let's move the object closer to the lens, between the focal point and the lens. The object distance is 15 centimeters, and the focal length of the lens is 22 centimeters. Where does the image form, and what is its magnification? Let's draw a diagram that shows our setup and the information given. We'll carefully trace the 3 principal rays. If you're doing this on paper, you'll want to use a ruler and graph paper. The principal rays diverge from one another as they move to the right. They converge to a point only if we trace them backward. That means the image that forms is virtual, and that we expect the image distance to be negative. We also see the image is upright and bigger than the object. That tells us we can expect the magnification to be more than 1. See all the information our drawing can give us? A good ray diagram is worth the effort. Let's move ahead and solve for the image distance d sub I. Our lens equation will again be useful. We're given the focal length and the object distance, and we want to find the third variable, image distance. We'll rearrange the equation because we want to find d sub I, the distance from the object's image to the lens. Now we plug in our values for focal length and object distance and calculate an image distance of negative 47 centimeters. Notice a couple of things about this answer. Number 1, it's negative, meaning the image is virtual. That's consistent with our ray diagram. Number 2, it's bigger in magnitude than our focal length or object distance. That also checks with the diagram. Now, let's look at the image magnification. Magnification is the ratio of the image height to the object's height. It also can be found by taking the negative ratio of image distance to object distance. Think back to our amazingly helpful ray diagram. The virtual rays that trace back from the lens to where the image forms begin at the top of the object, its height. and they meet at the top of the image, its height. It turns out that in normal cases, the ratio of image to object height is equal to the negative of image to object distance. We can write that in equation form like this. Image magnification is equal to image height divided by object height, which also equals the negative of image distance divided by object distance. So the image magnification in our case is negative 47 centimeters divided by 15 centimeters, which is 3.1. That means the image formed by this object and lens is a little over 3 times bigger than the object itself. We'll finish this closer look with an example of a different type of lens, one that diverges or spreads out rays of light. Like converging lenses, diverging lenses have a particular focal length, but diverging lenses are different in a few ways. The image they form is always virtual. The image they form is always upright, and the image they form is always smaller than the object. In this example, we have a diverging lens with a focal length of 40 centimeters, an object distance of 55 centimeters, and an object height of 18 centimeters. We want to know, what is the image height and distance to the image? First things first, let's draw a sketch of the given information, and then we'll do a principal ray diagram. Our sketch should look like this. Now let's trace in 3 principal rays, which will show us where to expect the image. We know that one ray goes horizontally until it reaches the diverging lens. The lens bends the ray upward, and we have to trace the bent ray backwards to intersect the first focal point, F1. The next ray goes straight through the middle of the lens. It isn't bent at all. The last principal ray is pointed toward the second focal point, F2. But rather than passing through F2, this ray is bent by the lens, so it runs horizontally. By tracing this ray backward, we see where it intersects the other 2 rays. Like we expected for a diverging lens, the image is virtual, smaller than the object, and upright. Try it for yourself. Press pause, take a couple minutes to figure it out, and come back and check your work. Okay, did you find the image distance is negative 23 centimeters? If so, great work. If not, let's take a look at it together. We use the lens equation so we can solve for the image distance d sub I. The object distance is given as 55 centimeters. This focal length magnitude is 40 centimeters. Since we're working with a diverging lens, remember that the focal length is negative. So when we insert numbers into our lens equation, the focal length f is negative 40 centimeters. This makes all the difference. Negative 40 centimeters times 55 centimeters divided by 55 minus negative 40 centimeters all equals negative 23 centimeters. This result is a great reminder how important it is to know sign conventions. They're not always easy to recall, but in long run, learning them will make things easier. Now let's move to solving for the height of the image. We'll find this out by using the fact that magnification can be found using 2 different ratios. First, magnification equals the ratio of image to object height. Second, it equals the negative of image to object distance. We can solve for the second ratio and then use that to figure out image height. The image magnification is negative 23 centimeters divided by 55 centimeters, which equals 0.42. That value is equal to the image height divided by the object height. So image height equals object height times 0.42. We know the object height is 18 centimeters. 18 centimeters times 0.42 is 7.6 centimeters. That's the height of the image. That's our closer look on lenses. For more physics in motion, go to our homepage where the entire series is available to you.